computer. Thank you very much all for being here at this AJS. The speaker today is Ariel Boiardi, former PhD student here at SISSA, and soon will be a postdoc at Okinawa Institute of Science and Technology. Everything is set up. Ariel, you can start. Please.
Thank you. Thank you, Roberto, for the introduction, and thank you, everyone, for coming to this seminar. And well, as Roberto said, I'll leave SISSA very soon, so I'm very happy and grateful to the organizer for allowing me to present my work today. In this talk, I will give a broad overview of my work here at SISSA, done during the last 3 years. And I apologize for those of you who attended my PhD defense. The slides are the same, but okay, I hope it will not be too boring. So as I was saying, my PhD project started on active materials and instabilities in active materials, and then other things were added, and finally we had to find a concept or a title for the thesis. So the global concept that should encompass all of what I did was that of non-reciprocity, which gives a conceptual framework that comprehends all of what I mean. So to understand what is non-reciprocity and reciprocal dynamics, let's start with reciprocity. In general, reciprocity relations. Reciprocity is a property of many physical systems, which encodes symmetry relations between, very broadly speaking, input and output of the physical system. In the simplest and most known case in continuum mechanics is Betti's reciprocal theorem, which states that given a linear elastic medium and two systems of forces called A and B, the work done by the forces A over the displacements produced by forces B is the same work that the forces B produce, for the displacement, the work of forces B on the displacement produced by forces A. And remarkably, this is regardless of inhomogeneities in the material and of the geometry of the material. So this is a very powerful property, and indeed it underpins many theoretical, numerical, and experimental techniques. Just to name one, the boundary integral formulation of linear elasticity and Stokes hydrodynamics, which is, of course, the basis of the boundary element method. But in some cases, this property can also be an obstacle, an hindrance for desired behaviors and functional behaviors. For example, in the context of low Reynolds number hydrodynamics, where the basic reciprocity result is Lorentz reciprocal theorem, this imposes strong geometric constraints on the motion of swimmers, because this known result due to Purcell states that in low Reynolds number hydrodynamics, any closed loop of shape change, so any cycle of shape change that and a closed cycle of shape change which repeats the same shapes forward and backward in time over a loop cannot produce motion in the fluid or cannot lead to propulsion and swim. And so this is why it's called the scallop theorem, because a scallop can only open and close. It has 1 degree of freedom, and over a cycle of shape change, it will repeat the same shapes forward and backward in time. And the theorem says that this cannot lead to swimming or motion in the fluid. Of course, scallops do swim, but they swim in a high Reynolds number fluid, so everything is okay. But the problem remains for very tiny swimmers, because at very small scales, inertial effects are negligible, and the dynamics is dominated by viscosity, and indeed, small swimmers, microorganisms, and cells have adapted the motion strategies and material properties in order to overcome this limitation through these shape changes, which are called indeed non-reciprocal, which are, for example, characterized by traveling waves or helical motion. And okay, why do these cells swim? They can maintain their motion through the conversion of chemical energy into mechanical work, which takes place in specialized motor proteins inside the constituent material. Similarly, in artificial active materials are polymers, for example, that are able to convert environmental stimuli such as thermal and chemical gradients or oscillating magnetic or electric field, and they can change their shape in response to such stimuli. These materials have gathered a lot of attention in the mechanics and soft robotics community over the last decades. And these are one of the topics of my work. But besides being able to replicate the motion of, replicate and imitate the motion of microorganisms, or for example, microswimmers, these materials, just like living ones, break symmetry at the constitutive level, because there is production of energy inside the material, which breaks symmetry, and thus negates the conditions for classical reciprocity results, such as Betti's reciprocal theorem, which I recalled in the beginning. And indeed, for this reason, these materials can also be studied in terms of how they support and propagate waves in a structure. For example, here is a robotic structure where you see that the wave is propagated forward or backward, depending on an actuation strategy. So this is an overview of my work and what I will be talking today. So this research was carried out along two main directions. So biomimetic motility and transgenerations, which are applications, ideal applications in the field of soft robotics, and finally, wave propagation in periodic structures, as I have mentioned. So, no, here, okay. Starting with this, as I've shown before, we have micro swimmers move in the surrounding fluid, overcoming the limitations of the reciprocal environment by non-reciprocal motions. And these motion strategies have been, as I said, imitated in artificial replicas. but in general requiring a time-dependent and complex actuation from oscillating acoustic or magnetic fields, for example. And we have shown both experimentally that this behavior can be obtained by minimal actuation, a constant actuation, thanks to flutter instability, which is this kind of behavior. This is a video from an airplane because flutter instability comes from the field of elasticity. And we see that from steady wind on the airfoil, we have the emergence of oscillatory motion of increasing arc. This is what we exploited to obtain our desired functional behavior. So, as I said, this work was both theoretical and experimental, and well, I'm very grateful to SISSA and to my supervisor for allowing me to expand my applied mathematics knowledge to more lab expertise. And okay, so the materials we use are these polyelectrolyte hydrogels. These are polymers polymers where inside the polymer chain we have fixed charges which create an electric imbalance and makes the materials susceptible to electricity, as I will show this. So the base polymer is based on acrylamide and with acrylamide, and the sodium acrylates introduces these charges. To produce these samples, this is a sketch of the sample. It's a very simple geometry, but we have to synthesize the polymer in a suitable way. And we use this photolithographic setup. So the polymerization reaction is started by a substance, a photoinitiator, which breaks apart when hit by UV light, releasing free radicals, which then start the polymerization reaction. So the photolithographic setup is this. We have a UV projector, which projects a stencil, like a rectangle, into this microscope. Then the light is focused by the objective of the microscope in this print setup, which is detailed here. So the monomer solution is placed between two glass slides, which are then kept together by two clamps. And so when the light hits the monomer solution, polymerization happens locally, and so we obtain our desired geometry in the plane. Okay, and everything is imaged, is guided by this camera. After the samples are ready, they are placed in an electrolytic cell, which is filled by sodium chloride solution in water, and an electric potential is applied from a power supply onto electrodes. Now, the samples are floating in this electrolytic solution, and when the electric potential is applied, we have the migration of the mobile ions through the cross section of the sample, so that we have a gradient of pressure in the cross section of the filaments, and which causes differential swelling, and thus the spontaneous curvature. So this is how these samples respond to electric stimuli. And then everything is imaged through a lab camera, taking advantage of the fluorescence of the sample. Now, let's see some preliminary experiments. to get an idea of this behavior. These are the electrodes of the electrolytic cell, and the sample, the ribbon, is placed in between the electrodes and parallel to the electrodes. When the electric potential is applied, we see the sample bends above the soft axis, so its motion is basically planar. And and the curvature, the final curvature that it reaches, depends on the electric potential. As you can see, the curvature is not constant across the sample. Here, and in particular, where the sample is aligned with the electric field, we have almost no curvature, and all the curvature localizes where the sample is crossed orthogonally by the electric field lines. Okay, so this dependence of the curvature on the current configuration inside the electric field is a key ingredient of this system. Okay, and these are the equilibrium, the final equilibrium configurations. But let's see how this equilibrium is reached. And so starting from different initial conditions, we see that for a given electric potential, the same curvature is reached. It localizes in different places, and it is reached with a characteristic time. So the dynamics has almost the same duration for any initial condition, for any applied potential. Okay. Let us now focus on this specific experiment. As you've seen, apply electric potential and the sample remains straight. So this is an equilibrium of the system. Still don't have any model for this, but we can state from observation that might be an equilibrium. So this is true until we apply a strong enough electric field, at which point we see that from the straight configuration, small amplitude oscillations start to emerge, which then increase in amplitude and lead the system on a periodic motion. And these are, of course, the hallmarks of a flutter instability or of a Hopf bifurcation, a supercritical order. After this transient, the system oscillates very regularly in a periodic way and swims in the surrounding fluid. I recall that all around here is the electrolytic solution, which is viscous fluid at this case. Okay. It swims, so its motion must be non-reciprocal in the sense that I have stated earlier. And indeed, it is characterized by a backward traveling wave. And an interesting observation is that it always swims towards the cathode of the electrolytic cell, the electrode with a negative sign, meaning hinting at the fact that we could be able to steer the swimmer around by reorienting the electric field. Now, a simple model that can be formulated for active rod in moving on a plane. I will skip the details here, but everything is until now is just balance laws for the case of a inertialess filament moving on a plane. We model the fluid structure interaction in a very crude way by these drag forces are just proportional to the velocity of the filament at each point. The main modeling ingredient is here, where we additive decomposition of the strain, so that the constitutive law for the bending moment is that the bending moment is proportional to the difference between the current curvature, theta prime, and a spontaneous curvature kappa, which encodes the activity of the spontaneous activity of the material. And for this internal degree of freedom, we have an additional equation, which represents, again, in a very simple way, the observations that we did earlier on the first experiments. Namely, we have target curvature, kappa e, which depends on the configuration of the filament in the electric field by this sin theta modulation, and the equilibrium configuration is reached in a characteristic time tau. This is a strictly phenomenological evolution law based on experimental observations, but it's good and it's very simple, but it is good enough to represent and to capture the main features of this behavior. Okay, so we have some parameters for the system. Some can be measured, some other are fit to numerical simulations. Okay, this is now interesting. What's interesting is that for model parameters compatible with the experimental conditions, we see that starting from an almost straight configuration, the virtual swimmer starts oscillating and then it moves on to a periodic motion. And okay, no, okay, and thanks to numerical simulations, we can also check that idea of steering the swimmer by orienting the electric field, as you can see here, by changing the orientation of the electric field, we can change the direction of swimming. This is just a numerical simulation. It is not a theoretical result, but we are investigating this point with a simpler model. Okay, so by dimension, okay. Well, now we have a model that from numerical simulations we see captures the features of the observed in the experiment, but we want to understand why these oscillations emerge. So, okay, I've anticipated that this is an instance of an instability, so we study the stability of the system around the trivial initial condition, trivial equilibrium. So we linearize the system in this configuration, leading to PGEs, lesson, and okay, and then we look for solutions that oscillatory solutions in time, leading to a cortical E, which can be integrated explicitly, and imposing boundary conditions allows to determine a characteristic equation for the eigenvalues of the system, for the eigenfrequencies of the system, depending on two-dimensionless parameters. And again, for parameters compatible with experimental conditions, we indeed find an eigenvalue which has a negative real part, consistent with the fact with the exploding oscillatory motion observed. Okay. We can then characterize the stability of the system across a range of parameters and find like length or different characteristics, different geometric and material properties of the sample if we expect it to swim. Okay, so we have seen here that directed swimming of an hydrogel robot can be achieved by minimal actuation without complex external control by offloading the low-level control task of generating the oscillations from an external control to the instability encoded in the physical system. And this leads, as a bonus, to a very lifelike motion as you have seen from the videos, and it has a remarkable swing performance in terms of the advancement per cycle of shape. Okay, that's it. I will go. I'll pass to the next. No. Well, okay. Another say along this line, we investigated a similar system because looking at nature, we see in some cases many filamentary organelles assembled into these ciliary carpets and ciliary structures, and their combined motion leads to very interesting and complex flow structures in the fluid. So we speculated, could we speculated on the possibility of composing some of these self-oscillating artificial filaments to obtain some interesting collective behaviors. Okay? And similarly to what I've shown, a single filament with a straight, with an electric field aligned to the filament can create these kind of flows, which are symmetric and aligned with the stimulus. So just as like the swimmer would change direction when reorienting the electric field, here, if the filament is attached to bottom, the flow reorients following the direction. But if you want to compose many of these units to obtain different motions in the fluid, we need to control at least some of the some characteristics of the dynamics of each single cilium, independent of the external stimulus. And okay, we have seen that by endowing the single filament with a natural curvature, we can obtain change in direction in the fluid without orienting the electric field. This was, well, the modeling is very similar to the previous one. We just have another additional curvature. And okay, there's a lot of interesting things that could be said, but I don't have the time. So skip it. But okay, the final result is here. And we can see that by increasing this natural curvature, we can change the angle at which each filament oscillates and produces the angle at which it oscillates, and therefore the angle at which the force is exerted at the base or in the surrounding fluid. And okay, the price to pay for increasing the angle is the fact that we reduce the performance of the absolute value of the force that we are able to generate. Okay, I went a bit fast on that because I wanted to talk about this final topic a bit more in detail. This is a bit different from what I've shown before, but again, the phenomenology and the arises, even if it is a completely different setting, arises from the same basic principles and in the same it can be explained in the same modeling framework. So let us now, this is again a beam, one-dimensional structure. Now instead of being free-floating in the fluid, it's just supported by two hinges. And okay, we just look at its linear response. Okay, so linear active beam, the same modeling framework, we have this fourth order term, and now an additional term that comes from the spontaneous curvature. And okay, this is looking just at the equilibrium of the system. Okay, so we can express this beam element by a stress-strain relation through this stiffness matrix K, which represents the relation between stress, in this case, torque at the end points, and the rotations at the end point. And when there is no spontaneous curvature, the off-diagonal elements of this matrix, of this stiffness matrix, are identical, consistent with the classical reciprocity results by that. But if we increase or decrease, if the spontaneous curvature is non-zero, this matrix becomes non-symmetric. And what does this mean? Well, let us, for example, start from a beam in this configuration and impose a rotation at the midpoint. And with no spontaneous curvature, as we expect, the response is symmetric about the actuation point, which is again consistent with classicals. But with the spontaneous curvature, we can asymmetrize the configuration in both directions by just changing the value of the spontaneous curvature. Okay. So this single element looks interesting. So let us compose a structure with a sequence of such elements with continuity at the boundaries of each unit cell. Okay, so the single element behaves as I have just shown, and let us consider a compound system, an infinite system. This structure can be solved explicitly, and I show how. So, by linearity across each unit cell, we have that the rotation at this end is just a multiplier alpha times the rotation at this end of the unit cell, and this comes from linearity. And then we have continuity, as I said. We have rotations and torques. We have no jumps at the interfaces between unit cells. And finally, the key observation is here. Since the structure is infinite, if we move one cell ahead, we still have infinitely many cells to go. So the proportionality constant for the next unit cell is the same as the previous one. And so we can determine an equation to find this alpha. And for a passive structure, alpha is a real number. Okay. Let's see what is alpha. We can determine these two values of alpha as the solutions of a quadratic equation. And when there is no activity, our change letter is key, but the same, these values of alpha are one the reciprocal of the other, meaning that, the two values of alpha represent the solution propagating to the left and to the right and to the left, respectively. So when the absolute value of alpha, if the absolute value of alpha is below 1, it means that the solution moving forward is decreasing, while an absolute value of alpha greater than 1 would mean that the solution to the right is exploding definitely. But we can save the situation by using the alpha, one of the two values that is smaller than 1, to build a solution going forward, and the other one, the one that is greater than 1, to build a solution going backward. So that its reciprocal is used, and we don't have blowing up deformations. And in this sense, with this interpretation, we see that when there is no activity, the two solutions are one the reciprocal of the other, meaning that the deformation is decreases symmetrically around decreases symmetrically to both sides. But if we change the value of the internal activity, we have again, as I previewed earlier, an asymmetric deformation. So here is the symmetric deformation, for example, on 10 elements, where we have prescribed rotation here, and then by increasing the value of K, so the spontaneous curvature, we can sustain the deformation on one side and make it vanish on the other. Okay. Even more interesting here is the dynamics of this system. So how waves propagate in this structure. So now we can write the dynamics of the morphoelastic beam. So our elastic beam with internal activity here, and with viscous damping around from the surrounding fluid. And okay, this is coupled with the usual evolution equation for the spontaneous curvature. So we again expand this in harmonic oscillations and lead to this, familiar fourth order equation. And again, we can represent the unit cell also in the dynamic regime by a transmission matrix, which encodes the way vibrations are transmitted from the left to the right of the unit cell, and the vibration both in terms of rotations and of torques. Okay. So this is a presentation for the solution across the structure. And okay, we could use this and proceed as we have done earlier with that identity trick. But another way is to use this expansion in block waves, non-block waves, because the exponent now is not real. So this are not classical block waves. But okay, the assumption is, which is okay, justified by the fact that we can indeed find these numbers explicitly, but we assume that the rotation and torques propagate with this constant, with this wave number k. And so combining these two transmission relations gives again a dispersion relation relating frequency omega and wave number k. In classic elastic and more in general conservative systems, this relation can be studied for real omega and k, but now the system is not conservative because we have dissipation from viscosity from the surrounding fluid, and we have energy input from the internal activity. So we need to consider this relation in full generality with omega and k conforms. And okay, with this expansion, which is explicited here, we see that the imaginary part of omega controls the amplification of the wave in time, and the imaginary part of k controls the amplification when moving from one cell to the one on the right. And therefore, the amplification factor going one cell left is just the minus imaginary part of K. Finally, real parts of omega and K control the wave propagation velocity. So, motivated by experimental measurements, we have to fix some parameters because we have so many. So we start by fixing this parameter, this value, motivated by these measurements, for which now these values are not fixed because we need exactly to know in which range we are performing the experiments. So I've designed dedicated experiments to measure the parameters, and we can talk about this later. But having fixed this, looking, for example, at omega, so now we look for solutions omega complex depending on the real K, we can characterize the stability of the system. Yeah, so we find a real and imaginary part of omega for all values of real part of K. Of course, the system is periodic, 2 pi periodic in real part of K. So this completely describes every mode that the system can oscillate. And okay, we find, for example, for this specific choice of parameter, we find that there is a region, so a continuous family of modes in which we expect blowing up oscillations. So again, something reminiscent of the flutter instability of the swing. And we can also completely, again, describe the stability of this infinite system across for all modes and or a range of values of T and the entire. The other analysis that we can perform is to look for the values of K, both real and imaginary part of K, when the frequency is real, which means that we are constraining the system to oscillate at a given real frequency, omega, and we look how waves propagate in space across the structure. So, okay, starting from the passive case, so the purely elastic case, again, we have 2 branches of solutions for K. One represents oscillations moving to the right of the system from the oscillation points, and the other branch represents the solution moving to the left. And we can see here the dispersion relation is symmetric, and indeed we see the oscillations propagate symmetrically from the midpoint where the oscillation is applied. When we increase the activity parameter, so this spontaneous curvature parameter, we see a lot of things changes. First, both real parts, the real part of both solution becomes positive, indicating a wave that both branches of wave propagate in the same direction. And also we see that the imaginary part, the dashed lines, become non-symmetric, indicating, as expected, a different decay behavior on the right and on the left. So, for example, oscillating at this frequency, we expect the red branch, which represents the solution to the right, to decay faster than before, and the solution to the left, represented by the blue line, to decay more slowly. And indeed, this is what we see from numerical simulations. Okay, if we increase even further this interactivity, we find a point where the imaginary part of K for one of the two branches becomes 0, indicating a wave that propagates without loss, so overcoming the dissipation due to viscosity. And this is what we see. We impose a rotation here, and the wave propagates without loss at the left, and decays very fast on the right. Okay, and then we can also inspect even more here. So we have, for example, here a mode that explodes spatially going to the left, and if we go a bit higher in the frequency, we get back to waves that are damped in space. So this block flow analysis is able to capture in completely the behavior of the system. And as we have validated by this simulation. Okay, now the difficult part is to perform experiments on this, because we have to impose an oscillation on a very small and soft object. Okay, so the experimental setup was designed to hold the hydrogen ribbon and to actuate it suitably. So this is the holder. The hydrogen ribbon is threaded across these slots here, and the central pin oscillates. So this central pin pivots on this pin here, and we have two permanent magnets attached to it, which are actuated by two couples of solenoids, actuated by two out of phase sine waves, which produce this oscillation in the central pin. Now, the statics, okay, very quickly, as we can see, the experimental result matches the theoretical prediction for the equilibrium shape of the periodic system. And here is a video of the dynamics. There is a lot going on in this, but you will see this pivot, this central pivot oscillating, and symmetric waves in the system at the beginning. And around this point, we turn on the electric potential, and the system asymmetrizes with different wave-bearing properties on one side and on the other. So here the system is symmetric, just elastic, and now the electric field makes enters, and okay, we see on this side almost no attenuation in the signal. The oscillations maintain the same amplitude over 4 unit cells, and on the other side, the oscillations remain very small. So this is an initial experimental evidence of the expected behavior for this system. So I'm very late, so I just close fast, but saying that polyelectrolyte hydrogens are a good material platform to study non-reciprocity in periodic systems, as they have a distributed and environmental actuation with a level of non-reciprocity that can be tuned. And we have seen unidirectional wave propagation, which overcomes viscous damping from the environment. That's it, and thank you for your attention.
Daniel, are there questions from here or from home, online? Please. Some curiosities about the experiments. Because I know you are performing now more experiments here in the lab, but concerning the last video you showed us, right?
Yeah.
You're trying to changing some parameters, changing voltages, just try to capture the same thing, but in, say, in a better way.
Okay.
Or what?
So both, meaning that I'm performing the experiment with one more unit cell, so it's larger setup, and I'm trying to basically reproduce this experimental. So having like different frequencies for a given or different levels of these two slides, let's say, different levels of activity and different frequencies to see that indeed we can have like lossless transmission, then have amplification, and then get back. So to really show experiments that these predictions match with.
So after both changing the voltages for the electric field and also the frequency
and also the frequency of temperature.
Other questions, curiosities? If this is not the case, we can thank Ariel again. Thank you for being here. Just a reminder that there is another seminar here, MATLAB seminar here at 4, and then tomorrow another MATLAB seminar at room 154 at 2 p.m. Thank you very much.